My name is Asser Sameh Taha. I am the team captain of Sky Thunder team. I am on my 4th year of university. My major is aircraft mechanical engineering. I've been on the team for 3 years now. Also, I have 3 years of experience with UAS technologies. On flight line, I'll be responsible of the pre-flight checks, the hand launch of the UAV, and I'll be the flight director.
Hi, my name is Omar Kamal. I am on my 3rd year of university. My major is aircraft mechanical engineering. I have been on the team for 2 years and I have 2 years of experience with the UAVs. My responsibilities on development team are the structure and airframe design along with manufacturing. On flight line, I will be responsible for any mechanical failures.
Hi, my name is Ahmed Tamer. I am on my 3rd year at the university. My major is aircraft mechanical engineering. I've been in the team for 1 year. I also have 1 year of experience with the UAS technology. My role on the development team is aircraft aerodynamic calculations. On the flight line, I will be in charge of any mechanical failures and the mechanical equipment.
Hi, my name is Ahmed Sharif. I am at the 3rd year of university. My major is electrical engineering. I have been on the team for 1 year. I have 1 year experience with the UAS technology. My roles and responsibilities on the development team is flight navigation, obstacle avoidance system, and autopilot handling. On the flight line, I will be in charge of ground control station operating.
My name is Sameh Nabawi. I am on my 3rd year at university. My major is electrical engineering. I have 2 years of experience in UAS technology, and that's my 2nd year on the team. My roles on the team are communication and networking. On flight line, I will be in charge of pre-flight checks and operating the imaging link.
Hi, my name is Muhammad Rabia. I am on my 3rd year at university. My major is computer engineering. I have been on the team for 1 year. Also, I have 1 year of experience with UAS technology. My role in the development team is automatic AUVSI algorithm. On the flight line, I will be responsible of automatic detection.
Hi, my name is Muhammad Badr. I am on my 3rd year at university. My major is communication engineering. I have been on the team for 1 year. I have 1 year of experience with the UAVs technologies. My role on development team is ground software development, and also on the flight line is manual detection.
Hi, my name is Karim Khattab. I am on my 4th year of university. My major is computer engineering. I have been on the team for 2 years. I have 2 years of experience with UAV. My roles on development team are programming, interoperability server developing, and modifying mission planner. On flight line, I will be responsible for interoperability server connections.
Hi, my name is Hamid Tariq Sulaiman. I am on my 4th year of university. My major is aircraft mechanical engineering. I have been working for the team for 3 years. I have 3 years of experience with UAS technology. My role on development team is UGV design. On the flight line, I will be responsible for the power management of UAV.
The team skills section shows the team skills at the beginning of the year and how it was improved by the end of the year. This year, Sky Thunder team has designed a new platform called Nisr in order to accomplish mission tasks at the AUVSI SUAS competition 2019. Nisr is an Arabic noun that means eagle. Nisr is a fixed-wing polar UAV hand-launched in takeoffs and belly landing. The takeoff weight is limited with a maximum of 14 pounds. We prefer the new polar configuration rather than last year's pusher one because we took into consideration the speed of wind as the suction of air coming from the propeller passes over the wing, which increases the speed of airflow for better lift during hand launch. During manufacturing process, the team's main goal was to manufacture the airframe with highest quality and lowest cost, as long as being sustainable. The main material used is balsa wood and plywood, in which we used super glue and epoxy to fasten parts. This year, the wing consists of 3 parts for the ease of transportation. The wing is made of spar semi-monocoque structure, where the main spar is made of carbon fiber. Computational fluid dynamics simulations, CFD, were conducted on the half wing to get the results for dynamic and static pressure distributions. The overall lift force on the half wing is 45 newtons, that is equivalent to 90 newtons on the whole wing, with lift coefficient of 0.337, which is reliable compared to the value of XFLR5 software, that is 0.236. Finally, the load was imported from fluent to static structure after adding sufficient materials, and the results showed that the wing withstands the load and is safe. We designed our parachutes by using the Newton's law equations of motion and making some assumptions to get the net acting force on the parachute as shown in this table. Given the parameters of UAV speed, wind speed, altitude, and system delays to our Excel sheet, we got the specifications of the parachute and the optimal dropping time and distance that is considered as an input data for Pixahawk for their drop command. Variety of parachutes from different materials and dimensions were designed and tested to choose the most suitable one. For the entire system power supplying, we use a 6-cell lithium polymer battery and another isolated 3-cell backup one for autopilot operation, with an electronic speed controller to control motor speed. For safety precautions, power is controlled using safety switch. We utilize Pixahawk 2.1 autopilot with IMUs, FMU, and triple redundant sensors, including GPS module for accurate navigation. The autopilot is calibrated using mission planner set. We utilize high-resolution camera Sony Alpha 6000, which is fixed without gimbal usage away from the motor to reduce vibrations. The camera is connected to an onboard computer or droid used for image transfer. Our communication system consists of 3 major channels. First, Wi-Fi link, where images will be transferred to the ground station using Bullet M5S transmitter and Nano station as receiver, working on 5.8 GHz. The images are sent to ground station operators for manual and autonomous detection. Second, pilot link, where safety pilot can have manual takeovers on the UAV using Futaba radio control transmitter and Futaba receiver connected to the autopilot, on board working on 2.4 GHz. Third, autopilot link. Data transmission is done using RFD 900 telemetry pair working on 900 MHz. And that's a brief for the entire communication system. A servo control door at the bottom of the fuselage is used for air delivery of the UGV, which is attached to a parachute for a gentle drop. This mechanism was tested with a dummy weight instead of UGV. For reducing the UGV system components and weight, we designed the UGV with Arduino system. In parallel, a commercial kit with APM board for autonomous navigation is used as a backup UGV, which is more effective for the mission. The main trade-off here is the weight. Electrical system architecture was designed as shown. Every unit was tested individually, then avionics system integration has been done, proving its reliability and suitability with our needs for appropriate flight performance. Now, after units integration and wiring, our aircraft is ready for mission demonstration. Softwares are used by 2 main groups. The mechanical group, where we utilize a reliable package of software such as Inventor and SolidWorks, which are used for UAV CAD drawings. XFLR5, which is used for aerodynamic calculations, stability derivatives. ANSYS, which is used for stress analysis and computational fluid dynamics. For the electrical group, we took advantage from our programming experience by modifying in the open source code of the AudioPilot interface mission planner to fit with our customized tasks as obstacle avoidance. Arduino is used for coding the Arduino program to control the UGV. Protos is used for Arduino connection simulations. Fritzing is used for PCB designing, which is utilized in the UGV. According to our team, the developmental tests are unit tests, integration tests, and simulation tests. A load test was conducted on the wing using a weight of 45 pounds to ensure that the structure can support the lift force distributed on the wing. Also, according to Shrink's method, a wingtip loading test was conducted. A motor thrust test was done in our lab to obtain the maximum possible thrust force. As safety comes first, throttle engaging while doing the hand launch is linked with a certain acceleration value beyond which the motor is triggered. For avoiding UAV steeply climb while taking off, pitch angle is controlled from the GCS. Manual tuning was preferred over auto-tune mode for higher accuracy, so PID values can suit with our aircraft design criteria, achieving more stable flight. Our UAV has proved high waypoint capturing performance by hitting 171 out of 187 waypoints over 15 flights. 130 minutes of autonomous flight has been conducted to ensure mission handling capability. For gentle landing, flare parameters are controlled using Mission Planner. Taking advantage of our GCS features, we utilize multi-vehicle control by only one station where we can monitor both UAV and UGV at the same time. This feature was then tested in the field and showed appropriate performance after changing the net ID for the two RFD pairs, avoiding interference between them. RRT algorithm is utilized for path planning and modified to fit with obstacle avoidance task, then implemented into our obstacle avoidance program, which generates an obstacle-free path with tolerance 20 feet away from the obstacle boundary. Python script, including DroneKit library, is utilized for the connection with the autopilot, flight data transmission to the avoidance program, and uploading the generated collision-free path to the autopilot. We modified the open source Mission Planner to fit our needs so we can monitor a real-time stationary obstacle avoidance with a dual visualization of the old given path and the generated path. 93 simulated obstacles were tested, avoiding 82 of them, giving an 87% accuracy. In the field, 43 obstacles were tested, avoiding 37 of them, giving an 86% accuracy. First, we did unit tests on the imagery and communication system, where we tested the process of sending and receiving images on the ground using Bullet M5 and NanoStation. Second test was an integration test during a flight at 115 feet altitude, and the results were a field of view of 134.5 times 88.6 feet along with 1.68 pixel per square inch. For ensuring the best image quality, the team's strategy was to build a lightweight mount of foam to the camera, which is located away from the motor to reduce vibrations that may affect the shutter speed to avoid image blurring. Furthermore, a suitable frame rate with the UAV speed was used for not missing objects. We tested our autonomous object detection and classification algorithm on last year's competition images and on extra shapes with the same dimensions and backgrounds of grass and asphalt. After 5 flight tests, we got the following statistics. On the GCS, a team member will be on charge of detecting objects and determining the characteristics manually to ensure the best coverage of objects. We tested our algorithm on 50 geotagged objects over 5 flight tests. A mobile was used to detect the accurate latitude and longitude of the shapes, and then they were compared to those resulting from our geolocation algorithm, and the average error was 40 feet. A unit test using a dummy weight on the dropping mechanism was done to check the servo response to Mission Planner commands. For integration, actual drop tests were done to check drag coefficient and material fabric of parachute, along with a simulation test to find the suitable air permeability. Consequently, many tests have been done, and here are their results. The team worked on controlling the UGV for the drive to location task using Arduino and autopilot systems in parallel to use the better in performance. The improved performance of NISR at every flight test really shows that we are capable of getting a higher full score than 60% at competition. Finally, we will show the flaws that have faced our team members and the corrective actions that have been taken.